Hello, this is the November 2021 Paper 1 Physics Multiple Choice questions. The first one is easy to ease you into it. Consider the statement below. The perpendicular force, this is a very key word, perpendicular. The perpendicular force exerted by a surface on an object in contact with the surface. Which one of the following forces is defined by the statement above? If you know your definitions, you will know it is A, the normal force. That is the perpendicular force. Frictional force is parallel, gravitational force is to the center of the earth, and the resultant force is what you get when you add all the forces together and are left with one force that has the same effect as the other forces. So if you know your definitions, this was the easiest 2 marks in this paper. Now, 2 balls of masses m and 2m, so I've got effectively a small ball and a big ball, are dropped simultaneously from the same height above the ground. Ignore air resistance. This tells you the balls are in free fall. Now it says, when the balls strike the ground, which one of the following physical quantities, so if it's a quantity, we can calculate it, will be the same for both balls. So we're going to drop these balls and they're going to drop downwards under the influence of gravity and hit the ground. So if we want to calculate it, let's have a think here. How would we calculate the weight? Well, the weight is equal to the mass times the gravitational force. The velocity, this we would have to use equations of motion, VI, VF, A delta T. Remember, they're going to be a projectile, so we would have to use an equation of motion here. Okay. The momentum is given by P equals the mass times the velocity, and the kinetic energy, your EK, is given by a half mv squared. So now, it says which one will be the same. The weight can never be the same because the one is m and the other one is 2m in mass. So this one will never be the same because one is got more mass than the other one. The answer is actually B, the velocity, because if you think about it, if we had VF equals VI plus A delta T, if we just use that equation of motion and my VI is 0 because the balls were dropped, A is equivalent to G, which is equal to 9.8. The time is the same. So if you have a look here, the final velocity for both of them will be exactly the same. So the answer is B. And this is what Mr. Galileo is supposed to have done when he dropped things off the Leaning Tower of Pisa to prove that things are accelerated by gravity. The momentum is not going to work because even though the V is the same for both the objects, the M is different. So the one will have a larger momentum. This one will have a bigger P, okay, because it's got a big M, gives you a big P momentum. And the kinetic energy will also be different because this one has got more mass. So this one will have a bigger EK as well. So the answer is B, the velocity, because it doesn't matter what mass you are universally accelerated to the center of the earth. Let's go to 1.3 here. The graph below shows how the momentum P of an object changes. Can you see P on this axis here with time T on this axis here? It says during which one of the following time intervals measured in seconds is the magnitude of the net force acting on the object the greatest? So now they've already plotted P on this graph and they've plotted T on the other axis. So this is already the mass times the velocity of the object. So if we look at our momentum formulas, we have F net delta T equals delta P. And the question is asking you about the net force. So if we take this equation and we rearrange it to get F net only, which is what the question is asking about, we get delta P over delta T. Now, anytime we have a graph, we always know that the gradient of the graph is of interest to us. Okay, so in this graph, the gradient is equal to the change in Y over the change in X, which for this graph will be delta P over delta T, because obviously this is the Y-axis and this is the x-axis. So what we are looking at here, if we want F net, we want to look at the gradient F net over here. We want to look at the gradient of the graph. So where is the gradient of the graph the greatest? And it doesn't have to be a positive gradient or a negative gradient. It doesn't matter because it just says what is the magnitude. So the sign doesn't matter whether it's a positive or negative. So we have to look here and see which section of the graph is the steepest. So where is there the biggest change in momentum for the same time interval? So here there's 20, between 20 and 0. Here there's between 20 and 10 in 1 second. Between 2 and 3 seconds, it's between 10 and negative 10. So this is also 20. And between 3 and 4 seconds, if you read it off the graph, it's between 20 and negative 10. So this is 10, 20, 30 little blockies. So the steepest gradient is between 3 and 4 seconds, which is answer D. Now, if we come to 1.4, it says a ball is dropped from a height above the floor. The ball makes an elastic collision. If we have an elastic collision, energy is conserved in an elastic collision. Okay, so it says at time t0 and bounces vertically upwards. So basically what we've got is we've got a ball doing this, hitting the floor, and bouncing back up, and because it's an elastic collision, it'll reach the same height as what it was dropped from. Ignore air resistance, so the ball is a projectile. It's in free fall. Which one of the following graphs shows how the total mechanical energy of the ball changes with time? And now this is the sneaky part in the question, because mechanical energy is actually the sum of the potential energy and the kinetic energy. And in an elastic collision, the energy, I shouldn't have put a K there, sorry, the energy is conserved. So what happens with the ball? If we were to look at the ball over here, say this is, because this is at time t0. If we look at the ball here, all of the energy here is EP, if we use the ground as zero reference. Okay, so this is here, the potential energy is at a maximum. On the floor here, the potential energy is 0 if the floor is our zero reference, but the kinetic energy is at a maximum. And if we look at the ball somewhere halfway through its flight, it's sort of half potential energy and half kinetic energy, okay? But the point is that at any stage, if we add these two together, they will be constant, especially if there is a mechanical collision. So the only one that shows the mechanical energy, which is the sum, you have to add them together, of the potential energy and the kinetic energy, the answer is B, because this is the only one that shows the mechanical energy being constant. Yes, the ball speeds up and slows down as it drops and bounces. It speeds up as it drops and it slows down as it rises up from the floor. But that is only looking at the kinetic energy. And the ball has a lot of potential energy when it's high and no potential energy when it's low. But the mechanical energy is conserved. It is the same. And so the answer is B. Now here's a nice question related to the Doppler effect, but with light instead of sound. Consider the two spectrum diagrams below. So here is the blue end and here is the red end. So whenever we want to look at something like this, okay, we should always remember the spectrum: red, orange, yellow, green, blue, indigo, violet. And this is the high energy, high frequency side, and this is the low energy and the low frequency side. So if we look at these two things, diagram 1 and diagram 2, we can see some spectrum lines. These are obviously like emission spectrum lines. And if we look at these lines, there's two together and one further away. Can you see everything has shifted to the right between diagram and 1 and 2. So this is red shifted. The lines have moved to the red end of the spectrum, which means if they've shifted to the red end of the spectrum, they're going towards a lower energy thing. So this is on Earth, and this is on the star. Okay, we only get a red shift or a blue shift if two things are moving relative to each other. There has to be relative movement. If two things are tracking each other at exactly the same velocity, you will not get a shift. But if they are moving further or closer together, they will show either a red or a blue shift. So it says to you, which one of the following can be deduced from the spectra above? Now, this is a red shift. A red shift is proof that the universe is expanding, and when things are expanding, things are moving further apart. So no, if it was moving towards the Earth, it would be blue shifted. If the star is at rest relative to the Earth, there is no relative movement. That's not going to work. The star is moving away from Earth, C, that is Y. And if the star and the Earth are moving towards each other, this will give you a blue shift. So the answer is C. Now 1.6, we can see here two little charged objects, P and Q. The diagram below shows the field lines for the combined electrical field. Now, before we go any further, let us think about what is an electrical field. And if you know your definitions, here is the definition for an electrical field. It is a region in space in which an electric charge experiences a force. The direction, remember it must have a direction, that's what all of these little arrows on this diagram are. They are showing you the direction of the electrical field. The direction of the electrical field at a point is the direction that a positive test charge would move if it is placed at that point. Now, anybody who's ever met me will know that one of my favorite things is like charges repel and opposite charges attract. So if we have a positive charge placed over here, it's going to go that way, okay, according to all of these little arrows that are on this diagram. So if like charges repel, it means P must be positive, and if they're being attracted to Q, it means Q must be negative. So this is very definitely an attraction diagram. Remember, if you have two positive charges, like charges repel, the field lines will make the shape like this. They will never want to go towards each other. Okay, so this is definitely an attraction. So we have opposite charges, and P is positive and Q is negative. So the answer here is D. And your definition is what is helping you do that. You have to know that the arrows show the direction a positive test charge would move. And as always, like charges repel. Now we come to 1.7. It says to you two identical spheres, P and Q. P, look at these lovely spheres. P and Q carry charges of plus Q and negative 2Q respectively. Sphere P exerts an electrostatic force of magnitude F on sphere Q. Okay, which one of the following represents the magnitude of the electrostatic force exerted on sphere P by sphere Q? The answer here is BF, okay? The force is exactly the same due to Newton's third law, okay? There is an equal and opposite force. Don't quote Newton's third law like that, okay? Do it by the definitions. But remember that there is an equal and opposite force. If you're not happy about Newton's third law, think about this formula here for calculating electrostatic force. F equals K Q1 Q2 over r squared. If I asked you to calculate the magnitude of the force of P on Q, you would just substitute into this equation, and get an answer. If I asked you to find Q on P the other way around, the numbers going into this formula would be absolutely identical. Doesn't matter if you P or Q, what you put into here, as long as you put in the Q and the negative 2Q of charge, you're always going to end up with the same answer. So it's due to Newton's third law, but if you get stuck, pull out the formula and say to yourself, what would I do if I put P exerting a force on Q? What would I want to do if I wanted to calculate Q on P? You're going to get exactly the same answer. So the answer is B, which is the force F. Okay, let's look at question 1.8. In the circuit diagram below, all resistors are identical. Ignore the internal resistance of the cell. Okay, so let's have a look here at the circuit here. It says which voltmeter will have the highest reading when switch S is closed. So if we have a look here at this circuit, let's just start here at the battery. If I redraw this in a straight line, I will come out the battery, I will hit resistor R, I will keep going, and then I will get a parallel circuit, and there's this other resistor R, and another resistor R, and then these will go together and go back. Here would be my switch, and then I would be back at the battery, okay, if I were to straighten this whole circuit out. So you can see what we have here is we have in series a parallel resistance. So here is the parallel resistance, and it is in series with this resistor R. So if we start thinking about the voltmeters, what is going to happen here? If we have a look here, which of these two has overall the biggest resistance? This resistor R will be the biggest resistance, and we're interested in the resistance because the current is the same everywhere in a series circuit, but the voltage can change, and the voltage will change depending on the resistance. If we put these together in a parallel circuit, remember that a parallel resistance is equal to the sum of the inverse of the resistances, okay? So this will actually be a smaller resistance, the total resistance. If we were to take these out and make them into one resistance, it would be a smaller resistance than this one. So if we have a big resistance for the same current, this one will have a larger voltage, and this one will have a smaller voltage if we pretended that this was a single resistor, okay? So what will happen here? We want the highest reading. The highest reading is going to be on voltmeter 1, this one over here, which is A. Also remember, voltmeter 2 and voltmeter 3, you can easily see that these two will have the same reading because resistance in a voltage in a parallel circuit is the same. And in actual fact, voltmeter 4 will actually be the same as voltmeter 2 and voltmeter 3. And if you do your practical, you should know this. So those are all the same. The highest reading will be voltmeter 1. V2, V3, and V4 should all have the same reading. So the answer must be A. And now we come to 1.9. In which one of the following electrical machines is electrical energy converted to mechanical energy? So anything that converts electrical energy to mechanical energy is going to be some kind of machine that you plug in the wall. Think about it. You get electricity out the wall and you use it to do work. So it is not any kind of generator. So anything that's got the word generator in it, that is taking, a generator does the reverse. It takes mechanical energy and makes electrical energy. So those two are gone immediately. A dynamo is exactly the same as a generator, so it's not that one. The answer has to be D, the DC motor. Now we come to 1.10. Which one of the following combinations correctly links an emission spectrum and an absorption spectrum to the energy transitions of an electron in an atom. Remember, when we talk about spectra, if we think about here is the nucleus of an atom, and we have, according to Mr. Bohr's theory, all of those little levels of the atom, which if you remember from grade 10, we were going 1s2, 2s2, 2p6, okay? When we are having energy emitted, it's when you go from a high level, a high energy level, that is a drop, to a low energy level. So something's got to happen to the extra energy. If you have got a high energy here and a low energy here, something's got to happen to the energy. It gets emitted. But if I have a little electron here close to the nucleus and I want to take it from this nice, stable, low energy place to the high energy place, I'm going to have to absorb energy. So the answer here is D. We emit energy when we go from a high to a low energy level, because remember, the energy's got to be conserved. Something has to happen to it. So if we go from high to low energy, we will emit light, and we will absorb light if we want to increase our energy. We take the little photons of energy out the light and go from a low to high energy level. So the answer is D, and that is the end.